Okay, let me try to share my screen. All right, fantastic. Okay, so let's move this here. Okay, how's that? Can everybody see my screen?
Yep,
Awesome.
we can.
Awesome. All right, well, hey, DataPhilly, Philly Pug. My name is Joe Papa. It's great to be here. Thank you, Rama and Mary and Ann, for inviting me to present tonight. Real excited to be here and talk about some cool topics with you folks. Before I get started, I just hope everybody is safe and sound, you know, with the given conditions. Personally, I'm located in New Jersey, in Red Bank, New Jersey. We are just about an hour away from Philly. You know, we've been to the Philadelphia Zoo and the area down there. It's just a great place to be. Love going there. You know, things are continuing to improve here in New Jersey. A lot of the restrictions are being lifted, and it looks like the cases are dropping. So I hope things are going well for Philadelphia and wherever you're located. Hopefully we'll get through all this soon. So tonight I'm going to talk about visualizing deep learning with Tensorboard and PyTorch. And I'm going to try to, let's see here. Going to see. All right, my dog is super excited about this, so hopefully you can hear him barking in the background. He's super excited. I'm going to just try to get the chat here. So if you can, before we get started, let me just tell you a little bit about myself. Before we start, just feel free to connect with me on LinkedIn. My tag is Mr. Joe Papa, and you know, I can send you the slides and the code, so don't worry about it. I know that this is being recorded and everything, but if you want to get slides and code, don't worry about taking too many notes or whatever. I can certainly send those to you. Currently, I'm the chief AI engineer at a small consulting company called Mobile Insights. Before that, I spent 25 years in research and development, working for a number of companies, including Verizon Wireless and Bell Labs, as well as leading artificial intelligence teams at Booz and Perspecta Labs. Currently, I'm the founder of INSPIRD.ai, where we do a lot of training and mentorships for data scientists and machine learning engineers. So encourage you all to reach out there and see if there's anything we can do to help you learn and improve yourself in this field. It's a super exciting field to be in, as I'm sure all of you share the excitement. It's just a wonderful, wonderful time to be in data science and machine learning and AI. It's just incredible what the technology is doing for the world. So let me jump into the presentation, and then we'll take some questions at the end. So basically, I'm going to cover two things in this quick presentation. First, I'm going to go over Tensorboard and what capabilities and what Tensorboard can do for you. And then we'll run through some code and some examples of actually how you would use Tensorboard with PyTorch, and we'll show you how to use that. And then we'll take some questions at the end. So before I get started, just feel free to just type in the chat. Has anybody here actually used Tensorboard before? If you have, just let me know in the chat that you've used Tensorboard before. Or PyTorch, if anybody on the calls has used PyTorch before. All right, Tejas, you have, awesome. Manu, haven't yet. All right, that's cool. Yeah, just let me know if you've used it before. If not, that's awesome. That's why we're here, to get exposure to things. Kostya, PyTorch, very cool. Very nice. Mary has tried PyTorch. Great. Yeah, I mean, PyTorch has just been an incredible framework for deep learning. I could say I started using it several years ago, and it's actually been very interesting to see how the framework itself has evolved. It's at a very stable point right now. So it's very, very useful. It's you know, certainly something if you're interested in deep learning, that is something that you should explore. So let's talk about Tensorboard first. So what is Tensorboard? So Tensorboard is TensorFlow's visualization toolkit. So TensorFlow, if you're not familiar with TensorFlow or PyTorch, both of them are deep learning frameworks or libraries that you can use to do deep learning development, research and development, mostly in Python. So those are pretty much the top two. If we look at popularity, you know, at this time, I think, you know, TensorFlow and PyTorch are right at the top, and they're really the two main ones. There are other frameworks as well, but the TensorFlow and PyTorch by far are two of the most popular ones. TensorFlow was the visualization toolkit for Tensorboard rather was TensorFlow's visualization toolkit. At the time that it was released, PyTorch did not have a visualization toolkit, but now PyTorch has integrated Tensorboard into its built-in capabilities. So now you can use Tensorboard with PyTorch as well as TensorFlow. Okay, so it's really, really powerful tool, and I'll run through some of the capabilities of Tensorboard, and then I'll show you how to use it with PyTorch. Okay, so what are some of the things that we can visualize with Tensorboard? Well, one thing that comes to mind is if you've tried to do deep learning research and you wanted to train models and see how those models are training and whether they're stable or not, you're going to look at the loss in accuracy over time as you train through each iteration or each epoch. And typically this is done at first by just printing out the text. So you can see over on the right-hand side here, or on the left-hand side rather, you can see that we're tracking loss. It starts off at 2.195 and then starts to go down. This is all great and everything, but wouldn't it be awesome if we could visualize this instead? Well, that's one of the key features of Tensorboard is you can visualize any scalars, and all you really need to do is save these scalars to a log file. And visualizing the accuracy and the loss during deep learning training is one of the popular ways to use this. So I'll show you how to do that in code in just a bit, but I just want to give you an idea of what you can do in Tensorboard. Okay, so we can plot out scalars, that's cool. Next, we can also visualize images. Okay, so here on the right-hand side, we show an example of the fashion MNIST data set, which is a common computer vision type of data set that has pictures of clothing. And you can actually use Tensorboard to visualize what the data would look like. And there's a lot of different things you could do as you're doing your research and development by having the capability to visualize images. You can also visualize text. You can play audio files as well. So as you're training and testing your models and you want to do some analysis on the data, you can use Tensorboard to facilitate that. So some of the things you might want to do is you might want to look at some sample training data and see if anything's mislabeled. For example, you know, you look over to the picture on the right and you see something that looks like a t-shirt. You want to make sure that it's labeled as a t-shirt. And once your model is trained and you're going to test it, you can look at the output data and make sure that for cases where maybe a classification fails, maybe you're mislabeling something, you can look at the actual images pretty easily just to see what the differences might be. Okay, so very powerful capability. You can visualize all kinds of stuff in Tensorboard, images, text, audio, and work with that. Another thing that's really, really powerful is the ability to visualize your graphs. Okay, so as you develop your neural networks and your neural net models for deep learning, sometimes it's a good idea to kind of look at these things visually just to make sure that, that they're built correctly, right? That the connections are made properly and that all of the parameters that you set are properly configured the way that you want them to do. So you can certainly print out models using PyTorch in text format, like you can do in TensorFlow. But being able to do this visually is a very powerful technique and supported by Tensorboard. Okay. So those are some of the things. I'm going to show you some other things that you can do in Tensorboard, but let me know in the comments. Do you think that these are things that could help you in deep learning research and development? And let me know if that's something, you know, if you're interested in deep learning, let me know that as well. So one of the things that might help with deep learning also is to visualize your weights and biases, okay, of your network neurons, and you could use that use the histogram features of Tensorboard as well. So you can plot out histograms, you can plot out the distributions of many things like weights and biases, and check for things like diminishing and exploding gradients, and see that you know, kind of what's going on a very visual basis. Okay, Rama, very interested in deep learning, very cool. And Quinn, you're an amateur deep learning researcher. Awesome, awesome. Yeah, I mean, there's the field itself, you know, has become quite popular recently. But still, when you think about deep learning in general, it's still, even though it's been around for decades, the uses and the ability to actually compute these things on processors and GPUs is now readily available, and it's such an interesting field to be in right now. So histograms, that's another thing that that we can do. Let's see, Tim, hobbyist at this point, but seems like the business sector is finally taking notice. Absolutely. I mean, when you talk about sectors that this deep learning can help, I mean, really, it's every single industry, every single type of business can be helped by this. Awesome. So we talked about a bunch of things that we could visualize. Tensorboard also has another very, very powerful feature in the fact that it logs all of the hyperparameters for you. And this is very useful when you're doing experimentation in deep learning, because you may try to build a model and train a model and see what the performance is using a set of specific hyperparameters. For example, you might pick a specific learning rate or a set of learning rates. You might pick you know, a number of layers, different model architectures or configurations. All of this stuff you can you know, typically you would change them during experimentation and run the experiment and see what the performance is like. Well, if anybody, you know, and share with this on the chat if you've been there before, anybody that's been running experiments or doing coding, it's like you get so involved in what's going on that sometimes you forget to keep track of, you know, what parameters you were using, what's the results you got for each experiment. I know I have many a times, you know, and sometimes you're taking notes and, you know, it's on a piece of paper that gets lost or whatever. Well, Tensorboard has a really awesome feature in which you can log hyperparameters associated with each experiment and each performance of that. So this way everything is kept track, you know, in files on your computer, and you can click on different experiments and see the visualizations that are associated with that experiment. So one example would be, let's say you run an experiment and you get, you know, a certain degree of accuracy, and now you want to go and look at the images that are misclassified. Well, there might be some differences depending on what hyperparameters you chose or model architectures. You can easily do that in Tensorboard. Okay, yeah, so I'm just looking at the comments now. Yeah, Tejas, that's all. It's awesome. It's really one of the it says that Tejas says that I didn't know we could use Tensorboard to play with hyperparameters. Would be super helpful. it's one of the most powerful things and useful things that I've used Tensorboard for. Super time saver. And yeah, Quinn, definitely done it through no paper. Absolutely been there. Okay, so one last thing I want to show you on the visualizations, and then we'll jump into the code, is you can also use this tool called the projector tool. And what this does is allows you to do 3D embeddings. And if you're familiar with embeddings, what embeddings do, I'm gonna bring up this website so I can show this live, hopefully. What you can do with embeddings is typically you have a large amount of data, whether it's large number of features or large vectors. Perhaps they're representing words, for example. Perhaps they're representing images. Whatever these large dimensional space of data is representing, it's sometimes difficult to view relationships between the data points. And having this projector tool here is very useful in being able to visualize that. And this projector tool is completely built into Tensorboard, and you can use this right from the Tensorboard tool. So I'm just gonna kind of show you this live. So here's the projector. If you go to projector.tensorflow.org, this is a little tool where you can play around what a projector is. What we're looking at here is we have this word-to-vect data set, which takes words and maps them into a 3-dimensional space, or rather a 200-dimensional space. That 200-dimensional space is now being displayed in 3 dimensions. So we can see, like, if we want to see what this word is, this point is the word configuration. You know, a word similar to it would be graph. I don't know how optical is related. But you can play around with this tool. You can drag it. You can stop it. You can see what words are similar to each other or close in this 3-dimensional space. Very, very interesting, powerful tool. All right. And that's also part of the projector tool in Tensorboard, so you can interface with that directly from Tensorboard. All right, so next I'm going to show you how you would write the code to implement this. So before I get started, just you know, kind of in the chat, let me know if you have developed or used Python before. How many people are really comfortable with Python? Just let me know in the chat. I would imagine that's a lot of the audience here, especially with the Philly Pug folks on board. Awesome. Awesome. Yeah, it's the nice thing about PyTorch compared to TensorFlow, and both of them are very powerful tools. I'm not here to kind of sell you on PyTorch, although that's the framework I would prefer. It's very Pythonic. So if you're you're used to creating classes and using instantiating classes and running objects and running methods on objects, it's very Pythonic. You'll be very comfortable with the API that is used in PyTorch. Awesome. So Kostya, Python all the way. Sayang, intermediate, awesome. Daniela, yes, great. Looks like a lot of Claude. Use Python regularly. Have used Keras, TensorFlow. Fantastic. And Gene, intermediate. Very cool. Very cool. Ooh, code contributor to Django. Awesome, Tim. That's good to hear. Wonderful. So you folks that are familiar with Python, this should come pretty natural to you. And I'll show you how it works. So what we'll attempt to do is I have slides on this, but let's attempt to kind of run this in a Google Colab Live, and we'll see how this works out, right? Love live demos. Okay, so I'll walk through this and I'll actually zoom it a little bit so you guys can see this a little better. Okay, so let me know in the chat, has anybody used Google Colab before? Or what's your preferred IDE? What do you folks that are familiar with Python, what do you like to use? Do you use VS Code? Do you use Jupyter Notebooks? Do you use PyCharm, Spider? you know, what are your favorite stuff? Okay, Akshay, PyCharm. Okay, very nice. PyCharm is very good tool. Let's see. All right, a lot of comments coming in. Awesome. Jupyter Notebooks, SpaceMax, Spider, Jupyter, Notepad, and Anne uses Notepad++, and she's not ashamed. That's great. Awesome. VS Code, Atom, Spider, Claude using Spider. Great. Yeah, these are all great IDEs. I've used most of them. I tend to use Google Colabs a lot just because it's very easy to share notebooks. If you haven't used Google Colab before, it's definitely worth checking out. It does have GPU capabilities as well. So if you want to run some GPU acceleration, which you know, of course, is a very big feature of PyTorch. You can do so very easily with Google Colab. So I encourage you to check it out. It's much, if you've used Jupyter Notebooks, it's very similar to Jupyter Notebooks, only you run it from your browser and you don't have to run anything locally. It's all run in the cloud on your Google Drive account. So very nice and convenient. Okay, so let's walk through an example. I'll just, the first cell here, we're gonna import the libraries we're gonna use. And the way we import PyTorch is we import it as torch. Okay, there's a little subtle trickiness there. If you're new to PyTorch itself, it's not import PyTorch, it's import torch. And that's just historical reasons behind the involvement of PyTorch from the torch library. And then the next thing we're going to do is we're going to import the neural network module and specifically the functional module to build our networks later. In the fourth line, we're importing the optimizers module as well. So we'll get to that. I'm not going to go through a lot of detail in deep learning tonight, or go through, you know, sort of specifics about deep learning. My main goal here is to show you how to put together a basic PyTorch program and then integrate Tensorboard with that program so you can display things in Tensorboard. Okay, so the key thing here is this line where you're going to import the summary writer class from utils Tensorboard. And the summary writer class is the only thing you need for Tensorboard. Everything that you do in Tensorboard is run using this summary writer class. Okay, so I'm going to go ahead and execute this cell, and we'll see that with Google Colabs, there's nothing to install. It's already pre-installed. PyTorch is pre-installed. Most of the libraries that you use for data science are pre-installed. We can print out the version. We see we're running 151. Okay, so let's, in the next cell, we're just gonna create some data. And so what I'm gonna do is I'm just gonna create some random samples. We'll call them X. And PyTorch uses this concept of tensors as objects. So if you're familiar with NumPy, it's like NumPy arrays, but they have a couple of extra features that are very powerful for deep learning and doing backpropagation. So the look of tensors, you could just think of them as multidimensional arrays or n-dimensional arrays, but it's a very powerful class as part of PyTorch. So we're going to set up some random data called X, and we'll compute another set of data called Y. And we're going to try to predict the function that we're using. In this case, Y is simply going to be the sign of X. All right, so this is the syntax that we would do in PyTorch to achieve this. And then we can use matplotlib to just plot it directly and see what the data looks like. Okay, so you can see here that if we just plot the data itself, it looks like a sine wave. Again, this is all just random. We're picking random values of X and computing Y based on the function sign of X. Okay, so that's our data. Next, we're going to just define a very simple neural net model, and we'll call it MyNet. And this is the syntax to do that. This is just a simple. All right, so we, as I was saying, we built our network and we instantiated our model. Okay, and then we'll just jump down to this this next section here. So this is the bulk of what we're going to do to train our model. Okay, so if you're not familiar with deep learning or the steps to train a model, that's okay. There's no need to you know, get lost here. The main important thing is, and I'll walk you through this, is we're going to build a writer using summary writer class, and then we'll call these methods which add the data to the log files. And as we add data to the log files, then Tensorboard is going to use those log files to display the data that we're sending to it. Okay, so in deep learning, we're going to want to define our loss function. For here, we're using mean squared error for our loss. As an optimizer, we're just going to simply use stochastic gradient descent here. And then we instantiate our writer for use with Tensorboard. We're going to use the add graph method to give Tensorboard our model, and it's going to be able to visually display that model. Then we're going to run through our training loop right here. We're doing a simple training loop with 10 epochs. We're going to execute our model and compute our predictions. We calculate our loss. We run back propagation. We run our optimizer, and then we zero out the gradients. That's a simple training loop for any neural network deep learning training process. Okay, we're also going to print out our loss and epochs per each epoch here. And at the same time, for each epoch, we are going to now log our loss value to the writer, the Tensorboard writer, using the add scalar method. Finally, at the end, we're going to use the add age parameters to save the hyperparameters to this experiment so that we can access them from Tensorboard. Okay, this is the basic skeleton that you need to do these simple features in Tensorboard. As you add other things and want to save more data, you would just use other methods at the appropriate places. So I'm going to go ahead and run this. It shouldn't take long to train. Okay, and we can see that the losses kind of bounce around a little bit there. That's okay. Finally, to run Tensorboard, it's very simple. It's just a couple simple commands. And the first command, this load extension, will allow you to run this in Jupyter Notebooks or Google Colab. So you could actually run Tensorboard as part of the notebook. Okay, you don't have to do that. If you want to run it externally, you would just run the following command from the command line. But we want to run it in notebooks, so we're going to load the extension. And then the next line here is the only line you need to run Tensorboard. Like I said, you run this in the command line. Or if you're using notebooks like we are in this case, we're going to run this directly in the notebook. Okay, so it should load. There we go, and there's Tensorboard. Okay, we can see here that the loss that we were logging, we could easily see what it looks like, move the mouse around over particular values. We can change the smoothing factor if we want to smooth it. There's a bunch of things that we can do here. So that's at the Scalars tab. If we go to the Graphs tab, we'll see what our network looks like. And you double click on these boxes and it will show you what the network. We have a simple fully connected network with 3 layers. We can see that looks right. If something was hanging off the side here, we would know that easily know that there was an error. And finally, we have our age parameters that are logged here. And if we had other cases where we had different age parameters, we would have separate lines here for each age parameter. So that's really a basic overview of Tensorboard. There are so many other tabs that you can use. I'm not going to have the time to cover them all here, but I encourage you to go and explore this and try this out on your own and see what you can do with Tensorboard. So we'll just close this out. Yeah, so here's a list of all the different methods for the summary writer class. like I said, you can actually add videos, you can add embeddings, age parameters, so forth. All right, so that's basically all I have. I appreciate all of you for sticking with me through getting booted off of Zoom, and hope you learned something, at least got a little bit more exposure to the capabilities that you can do with Tensorboard and how easy it is to use them with PyTorch. Again, reach out to me on LinkedIn if you want a copy of the slides or a copy of the code. Be happy to share that with you. And best of luck to you.
All right. Thank you so much. That was really interesting talk. For somebody, I've used PyTorch. I've tried PyTorch, but I've never tried Tensorboard. So this will be interesting. You've definitely I've done a lot of R, so you've definitely kind of rekindled my interest in going back to Python. I think you answered most of the questions and addressed most of the comments in the chat live. So you made my job really easy. But I think there's just a couple of questions that kind of struggling here. So there's one when you were showing the projections, and there was a question, what type of projection was being used there? Is that TSNE or something similar? And there was a similar question from Tyler, what does the custom option look like? You know, there were options like TSNE, PCA, custom. What does the custom option look like? So those are the two questions fairly related with the projection.
Okay, yeah, good, great questions. Yeah, so the projection tool allows you to specify the algorithm you want to use for the reduction. So I'm not sure what it uses by default. It could be TSNE if you saw that on there. I'm sure there's other ones and other different types of algorithms. To be honest, I'm not exactly sure what capabilities the custom provides you, but I would imagine that it's a way for you to use a custom algorithm to do the dimensionality reduction from whatever number of dimensions you have down to 3D space.
All right, thanks. And then one last question from Kostya. Can you save, when you were doing the, showing us the Tensorboard demo, the logs that you generated, are you able to save all those logs as a file so you can go back to it and look at them?
Yes, absolutely. So if you run this locally through Jupyter Notebooks or through your IDE, it will automatically get saved to your local machine. If you're using Google Colabs, you would have to, there's a couple functions you could use. It's easy Google of what they are, but you would be able to download those functions locally. I'm sorry, download those files. In fact, the entire directory, they're all saved in a directory. You can download that whole directory to your local space.
All right, excellent. I think that covers all the questions. Thank you so much. That was an amazing presentation. And of course, at the end of the second speaker event, we'll have an interactive session. So if anybody thinks of any questions in the meantime, you can ask after that. Thanks again, Joe. Great talk. Awesome. And now I will hand it over to Corey, if you're ready to take over.
All right, hello everyone. Let me try and share my screen. All right, how is that? Can everyone see the slides?
Yep, that looks great.
All right, awesome. So hey everyone, I'm really excited to be here today to present on one of my favorite topics, which is self-programming artificial intelligence. And I want to start this off with a simple question. Is it possible for a computer program to write its own computer programs? So just to give you a little bit of background on myself, my name is Corey Becker. I'm a senior software developer at Bloomberg. I develop web applications and web services, but my core passion in computing has always been artificial intelligence and data science. I am also the author of the book, Building Voice-Enabled Apps with Alexa, which is my first published book in 2017. It talks all about how to create software for the Amazon Echo. Is everyone familiar with the Amazon Echo? Does everyone own an Amazon Echo? Maybe it's a paperweight on your table? I don't know. But I wrote a book about how to create apps for it. So you can talk to it, make it do things. The book is really interesting as the entire first chapter goes all into the history of conversational UI and chatbots. So is anyone familiar with one of the earliest chatbots, Eliza? So Eliza is a chatbot developed in the 1960s as a psychoanalyst. And it's one of the first examples of where people actually believed that they were talking to another human instead of a computer. It's also one of the first examples of a program that was capable of performing in the Turing test. So there's some very interesting things coming out of the initial conversational UI and chatbots that were developed back in the 1960s. Now, I consider myself an AI enthusiast. So I've always been fascinated with artificial intelligence, especially the concept of a computer program being able to create its own computer programs. So now I realize that a lot of us on this call today are software developers or programmers working in the industry, or perhaps you're studying to become a software developer or programmer, and you might be saying to yourself, well, gosh, if computers could write their own software, does that mean I would be out of a job in the next 12 months or something like that? Well, that may or may not necessarily be the case, as I will get to later in this presentation. But regardless, one of the techniques that I've experimented with that has yielded some amazing results is with the use of genetic algorithms. Okay, so genetic algorithms are a branch of artificial intelligence that deal with simulating evolution over thousands of different genomes, each to produce the best offspring most fit to solve a particular task. So in the case of a self-programming AI, that task is generating computer programs. Now, I like to think of this concept as the infinite monkey theorem. Has anyone heard of the infinite monkey theorem? So if we were live, this is where everyone would probably start laughing. So the infinite monkey theorem states, you can Wikipedia this, it's a real thing. If you have 100 monkeys banging on 100 typewriters, they'll eventually write a complete work by Shakespeare. Now this sounds ridiculous. How can a monkey write a play by Shakespeare? But think about it for a second. Given infinite time and space, wouldn't you all agree that at some point, one of those monkeys will hit the first letter on the keyboard that corresponds to the first sentence in the first word in a Shakespearean play? I think we can all agree that even randomness, that would happen. Now, take that one step further. Given infinite time, infinite space, wouldn't one of those monkeys end up hitting 2 consecutive letters in the first word in the first sentence of a Shakespearean play? So if we extrapolate this out to its final conclusion, given unlimited time, one of those monkeys surely will end up typing out a complete work by Shakespeare. Now, we don't have infinite time, so we need a way to speed this up. So what if you were able to give the monkeys a banana every time they type the correct letter in the sequence of a Shakespearean play? Perhaps you could guide those monkeys and that generation into a final solution that you were trying to build. And that's exactly the idea behind program synthesis. So program synthesis is simply computer programs that can automatically generate their own computer programs for a specific goal. Now, since the very beginnings of artificial intelligence, this problem has been considered by some to be the holy grail of computer science. So that's a pretty powerful statement. How can you say that? Well, just imagine what computers could do if they could write their own software. It's pretty amazing, and we're going to see some of these little tiny baby results later in this presentation. Now, program synthesis can be done today in many different ways, such as neural networks, deep learning, which we were just talking about. Thank you, Joe. Abstract syntax trees, programming by example, another fascinating topic in program generation, and as we're about to see, genetic algorithms. So in the case of using genetic algorithms for an AI to write software, a programming language that's easy enough for the AI to manipulate is required. So the selected programming language for this project is a very strange and esoteric language. In fact, it's known for being so difficult for humans to understand and especially to use. However, it's ironic because this programming language is exceedingly great for an AI to use with a genetic algorithm to generate programs with. So this language has 3 key characteristics that make it perfect for this particular task. The first and most important is that this programming language is Turing complete. So a Turing complete programming language means that it's theoretically capable of solving any computational problem in the universe. Okay, that's a bold statement. So by extension, an AI that is using a Turing-complete programming language to write its own programs can itself create programs that are theoretically capable of solving any computational problem in the universe. Okay, so we've opened the door wide open for our AI to be able to generate programs to solve any task that's necessary. The second key characteristic is that this programming language consists of just 8 instructions. That's it. You're looking at it right there. You're looking at the entire programming language. The brackets, the plus, the minus, that's the entire thing. And this makes it easy for a genetic algorithm to reduce the number of possibilities when it's generating programs. And of course, this leads to the third one. It's easy to build an interpreter for and to expand upon. And these are the key conditions that allow a genetic algorithm to use this successfully. So the way that this works is to generate a program, we first create a genome. The genome is encoded as an array of floating point values. Each of those floating point values will map to a specific programming instruction in a language. We then convert each list of floating point values into a program, execute them, and then rank them according to fitness. Fitness is judged based upon the output of the program, such as ASCII text, or perhaps behavioral characteristics, such as values of variables, or iterations in a loop, or other aspects of the program. The best fit programs will move on to the next generation to create child programs that get better over time. At each generation, we apply evolutionary computational techniques of roulette selection, crossover, and mutation. I'm going to show you these in just a second. And those help create the next generation of programs as we continue on. Just a second. There we go. Okay, so here's an example of constructing a genome. So you can see here at the top, we have a list of floating point values, right? And at the bottom, we have an actual program. So notice that each of these floating point values maps exactly to one instruction in the programming language. So as an example, I can't see you all, so I can't use my hands on a blackboard, but you can see how the value 0.1 maps to that open bracket, right? It just so happens that that open bracket is actually a begin loop command. Similarly, the plus sign maps to 0.6, or rather 0.6 maps to the plus sign. The plus sign is an increment operator that will increment the value in memory to the next value, and this is how the program works. In this manner, now initially, these values, of course, will be all random. That's how we start the entire population. So most of these programs that get randomly created will simply crash and burn. They'll fail right off the bat. However, one or two of them in a large population, just like the monkeys, will manage to do at least something. They'll output a character, maybe in the upper ASCII range. Maybe they'll start a loop iteration. Maybe they'll increment a value. They'll do something. And it's those programs that can be measured with a higher fitness that will move on to subsequent generations to create more programs. So how do we create the next generation of programs? Well, we apply an evolutionary computational technique of crossover first. You can see here's an example of crossover in this slide. So we have a parent genome at the top and a child genome below it that's being generated. The child genome is receiving the first 5 instructions from its parent. In this manner, we can carry forward beneficial traits of programs in a generation to future generations to continue on. The child will also receive, via crossover, another few genes from another parent. And this is how these genomes, quote, combine together to create children. We also apply mutation. You can see this in action on the right side. So we have a floating point value, remember each maps to an instruction, of 0.9 that is then being mutated to 0.8. What this ends up resulting in is the instruction, which is actually a shift up address instruction, is now changing to a downshift address instruction. And this changes the behavior of the program. Now, if this turns out to be a beneficial quality, then this child will have a higher fitness score and you have a breakthrough and it will move on to create more children. If it's detrimental to the program, maybe it makes it crash now, that child has reached an evolutionary dead end and it will be removed from the gene pool and other genomes will continue on. So once we do have a series of programs per epoch, we rate them and rank them according to their fitness. So only the strong survive, as this slide shows. You can see how the top program is removed from the gene pool, while the bottom one continues on to produce more children and get better and better over time. So why was the top program removed from the gene pool? Well, if we look at this, if we look at that program and you understand the language a little bit, the first instruction is an input operator. There's nothing wrong with that. The second instruction is an end loop operator. So what will actually happen is an exception will be thrown. So this program executes one step and then crashes. That's why it was removed from the pool. It probably has a fitness score of 0. The second one, however, if you look at this and you know the language, it's actually a valid executing program from start to finish. In fact, that program will take 2 characters from input and then output it. And that will have a fitness score much higher, which will continue on. All right, so what everyone, of course, has been waiting for is show me the results, right? Does this thing actually work? Do I have anything to worry about? Is my job in danger? Well, let's take a look. So my research has shown that the system is capable of creating programs completely from scratch. It's created programs to write hello world. It's created programs to perform addition and subtraction while asking for input from the user. Quite incredible. You'll see this in just a second. It's created programs to reverse a string. Can you write a program to reverse a string? You probably can, but what if you just started learning a program 5 seconds ago? Well, that's what this is doing. It's created programs for multiplication, user input, outputting the Fibonacci sequence from 2 starting values, even printing out bottles of beer on the wall. I'm going to show you that in a second. It's quite incredible. So let's take a look at the actual screens from this. So here's one of the first programs that it wrote. This was one of the earliest generations of AI programmer of this system. It was instructed to create a program that could simply output the word hi. And what do you see here at the very bottom? It is indeed output the word hi, followed by a bunch of gobbledygook after that. We can ignore all that stuff. Don't focus on that. Focus that it did indeed output the word hi. And there's the program highlighted as well. If you were to actually take that code and execute it in an interpreter, it would indeed output the word hi. Now, this is a really good example of be careful what you wish for. Be careful what you ask the AI to do, because it just might do it. So it was asked to output the word hi. What did it do? It wrote a program that does exactly that and a bunch of other stuff too. Now, if that other stuff happened to be take out the trash, cook eggs in the morning, or maybe something else, it would go right ahead and do that as long as it achieved the goal of what you asked it to do. So let's take, this was generated in 1 minute. It took 1 minute for the program, for the AI to learn how to program and write this. Here's another example. It was asked to write a program that outputs the word hello. That's exactly what it did. It wrote a program that outputs hello, followed by a bunch of other ASCII character gobbledygook, and then what happens? A Stack Overflow exception. So this is actually interesting. This was generated in 29 minutes. So the AI actually took advantage of that Stack Overflow to terminate execution of the program. Otherwise, it would be in an infinite loop, which would have a lower fitness score. So it just so happens that I was not penalizing programs for crashing in an exception. And because of that, the AI realized this, took advantage of it, and decided, hey, I will output what the human's asking me, and then I will terminate myself by throwing an exception. This is equivalent to having a robot that brings your newspaper in the morning and then blows up because it's like, I achieved my job. Okay, that took 29 minutes. Here's an advanced example. This is quite incredible. So here the AI was asked to produce a program that takes a string input from the user, okay? It has to store each of these characters in memory in variables. Then it was instructed to output hello followed by the input. It produced this program you can see above. This is a slightly more advanced version of the AI. This took 30 minutes. Notice how clean that program looks. So things are looking a lot different than the other programs as it became more advanced. you can see that I don't even know what that program is doing looking at it, but it does indeed start a loop, which starts accepting input from the user, followed by being able to output the word, the static string hello, followed by the variable content. Here's a program that took 10 hours. This is a much more advanced version of the program. Up to this point, it could only output short strings. However, here it's actually outputting a much longer string of I love all humans. Very nice AI to output something like that. That took 10 hours. And here is a much more advanced version of the program. There's a lot going on here. This program is bottles of beer on the wall. If you're familiar with the camp song, so the AI had to write a program that would count down. It would loop from 100 down to 0, or 99 in this case, down to 0, and output the number followed by the text, bottles of beer on the wall, for each iteration. So what do you have going on here? Number one, it's taking input from the user for the starting value. Number two, it needs to store that value as an integer that can be decremented within a loop. Number three, it needs to iterate in a loop. It needs to know how to create that construct. Number four, it needs to output text that's quite long for this program to be able to output. And number five, it needs to know when to terminate. So it's got a lot going, not to mention it needs to do concatenation of a numeric value with a string. So it put all of this together and it took 33 minutes. I was pretty surprised happily when I saw that one. I just want to show some close-ups before I get to the end of this presentation. So you can see here's a program for hello. You can look at this. I have no idea what this program is doing. If you look at this, it looks ridiculous, but it actually prints out the word hello. This was generated in 29 minutes. Here's addition. Your guess is as good as mine. I've been doing this presentation and this work for quite a few years now, and I still don't really understand how this performs addition, and yet it does indeed perform addition. This is a valid running program. This was generated in 45 minutes. You can input two values, it will add them together and output it. This outputs the Fibonacci sequence from two starting input values. What? I mean, look at this thing. The only thing I can determine from this, the first instruction, a comma, is indeed a user input command. The second one is an address shift up, which will make a new variable. And the third one is another input command. The rest of it, your guess is as good as mine. That took 7 hours. So it's pretty amazing to see what the AI has been able to do. And there's a lot of potential in a system like this. So I've been writing software for quite a number of years, and I've always felt it's just something that humans shouldn't be doing. Humans shouldn't be writing code. Humans should be designing programs. Computers should be writing the code. So I envision a future where humans design a program, they design a task or solution. They then give the design to the computer. The computer takes the design and writes the actual code to implement the software. The human can then write a design for a more complex problem, a more complex solution, and hand that to the AI. The AI can then use the prior solutions that it's generated as building blocks and put those together and assemble them, sort of like these gears that you see on the screen, into a larger solution. And in this manner, an AI would be able to create larger, more complicated program solutions for things like web applications, databases, word processors, calculators, games, and much more. In case anyone is still not quite believing, I ran the program today, shortly before presenting, and asked it to create a program that wrote this text you can see right here. I did not use Photoshop. This is not Photoshopped. You can try running the program yourself if you don't believe me. This was generated in 60 minutes. It did take 60 minutes. And with that, I will put up there's my info. If you're interested in learning more about this topic or my research work, my URL is right there. I go into an extensive description of my work on the blog. I also have a research paper published on Archive, which you can find via that blog as well. Add me on LinkedIn. Add me on Twitter. I am very friendly. I love talking about AI. I'm very passionate about it, and you can find other topics like this on my blog as well. And with that, I guess we'll open the floor for questions.
Great. Thank you so much, Corey. I'm scratching my head. I'm a little creeped out at the same time. I'm intrigued by this talk. So we had several questions. These are not in order. One of them kind of fit better at the end. So the first question is, how do we evaluate the fitness of a sample program to decide which one to eliminate or keep?
How do we evaluate the fitness of a program? Okay, that's a great question. Excellent question. Thank you for answering that. So the way that this is done is the human, myself, essentially writes a unit test, okay? So you provide example cases, example test cases for what you want the program to do. If you want the program to output text, you would give example cases of the text that you want. If all you want is a static text like hello, you would just give it the string hello, and there's a way of giving it to the AI, and it will generate that string. If you wanted to do something more complicated, such as add two numbers together, you would give it examples of two numbers and the answer. So you would give it 2 and 3 and then 5. Then you would give it 3 and 1 and give it 4. Maybe give it 12 and 2 and give it 14. And then at the end of generation, you hope that the AI is able to generalize on those examples and create a solution that not only solves those specific examples, but solves all examples that you give it across a range. Does that answer the question?
I believe so, but if the person who asked it is still unsure, you can go ahead and unmute yourself and clarify.
Yep, that answers that. And I was wondering, like, how would this be different than from a data-driven or a loss-based modeling approach? Because essentially what we are doing here is just feeding it with some data where we have the inputs and the appropriate outputs which we need from the system. And we are using some kind of reward-based system along with some random behavior. So how would it be different from all these modeling methods which we already know?
Well, the modeling methods don't generate software, right? They can't generate reusable software. However, I think your question actually brings up a really good point about other methods for generating software. So there is research that uses neural networks and deep learning, which, as you were alluding to, is certainly modeling to generate programs. Even to generate abstract syntax trees of a programming language that can then be executed. So the key here is that we're not building a static solution. We're having the AI build programs that are dynamic, that can take input and give output from different values that's reusable. So one of the ideas that I had, for example, when I started asking to generate addition and subtraction, was could I ask the AI to create a calculator, right? Now I know that there's hundreds and hundreds of calculator softwares out there, but if it could create a calculator, it could create something maybe that doesn't exist yet. So this is really the idea and the difference behind a static machine learning model compared to a dynamically driven system that generates software.
Yeah, thank you. Thanks for the clarification.
Yeah.
There was another question. This is for me, actually. Do different computers interpret the 8 base characters differently? So for instance, if you ran the hello Corey, hello fill in the name that you've input program on one computer, is it gonna fail on another system, or is it gonna work for every computer that you run that on?
This is what's incredible about this. It will work on every computer that you run it on. It is an actual programming language. It uses an interpreter and compiler. There are many interpreter and compilers for this language out there. You could run this on Linux, you could run it on a Mac, you could run it on Windows, you can run it in the browser, and it will indeed execute the program successfully as long as the interpreter is correct. It's, for example, generating Python code or generating C++. In this case, it's generating a different programming language.
Cool, very cool. Another question. How long have you been exploring this research topic? Were you inspired by the lecture on the evolutionary algorithms from the Udemy AI nano degree? I just went on your LinkedIn and saw that you completed it. I did too, says Kostya.
Awesome. I love online courses. I just finished it. Yeah, I just recently finished the artificial intelligence course on that. So I have been doing this research for close to 10 years now. So it actually predates, I think it predates Udacity. But as I mentioned earlier, I've always been very fascinated and passionate about artificial intelligence. I actually originally got into AI through interest in games. Star Trek helps too, like Deep Space Nine, or Captain Janeway all the way. But yeah, so gaming, things like that got me interested in this. And then I just couldn't get the idea out of my head of replacing us, of replacing programmers. I know it sounds awful, it sounds evil, but I promise I don't think we would be out of jobs. I think it would just change into something else. But I would really love to see a future where we don't have to write software anymore.
Thank you. Another question, maybe I missed this, but what is the input that you need to provide to be able to generate the Thanks DataPhilly program?
Thanks, DataPhilly. Okay, so, well, that was actually an easy one. So because I was generating it this morning or yesterday, so I didn't have a lot of time. So that one's actually a static string. The system can generate static string programs in a very short amount of time. And the input is very easy. All you do is you just give it the string that you're trying to generate. I just provided it with literally the string, thanks DataPhilly, and asked it, write a program that will end up outputting this string. Now, it's not actually taking the string, it's generating the string character by character, and then writing a program that will execute that and print it.
Great. Another question, do you expect ethics implications as this advances?
Can I say no comments? Ethics, I don't really, I try not to go down that route too much as far as ethics. I leave that to people who know more about that than I do. You know, I think there's plenty of people out there that are working on responsible artificial intelligence, responsible machine learning. There are some very dangerous things that can absolutely be done with AI and machine learning. I think it's different than what most people think. That would be a completely different talk, but I do believe that privacy and governance of AI is probably one of the more pressing matters that we are looking at in the very near future. You're seeing this happen from Facebook and Google and Instagram and Twitter. When you log on and you're starting to see ads and you're wondering, were they listening to my iPhone? How do they know that I was thinking about looking for an apartment in Philadelphia? How do they know that I was talking to my friend about shopping for clothes? So why do I bring these things up? These are related to AI. They're not listening to your phone. What they're doing is they're using machine learning models based on various artifacts that you've left, such as searching on Google. And with AI, they're able to come up with incredible likelihoods that this is what you were probably looking for. This is what you were probably thinking at this time on this day. That's the dangers I see with AI. Generating a program like this, having an AI generate software, I mean, the ethical implications could be what? Someone might create a virus, perhaps. That's in the research paper. I do talk about that a little bit. And really, containment is the way that you protect, but that's more so about during the generation process. It's quite possible that the AI could generate a program, one of those genomes, in the process, in the middle of the generation, that could end up crashing your computer. Or it could create a program accidentally in the middle that formats your hard drive or overwrites your boot sector. These are possibilities. If you gave the AI access to the internet, which I never have, then it could theoretically generate a program that could DDoS a website, right? This could all happen in infinite loops within the generation of your program. But since you're running it in an interpreter with a limited subset of commands, you're obviously limiting the I don't want to say damage, I want to say the range of capabilities that it can do.
Thank you. We have a couple more questions, and then we can open it up for just like for if anybody has any more questions for Corey or for Joe that they've thought of from the last talk. Are you able to run these programs on a laptop? It seems like it could be heavily parallel. I'm terrible at saying this word, parallelized.
Okay, so those are two different questions. The first question, can this be run on a laptop? Yes, it can be run on a laptop. In fact, I ran the program that generated data. Actually, I ran almost all of the generation on a laptop, although some of the more complicated ones were run on a desktop. The second question, however, and I assume you're asking the system, right? Not the programs that it generates. The programs that it generates can be run anywhere, even in the web browser. As long as there's an interpreter in the web browser that can do that, just like Python code. The system itself, that can indeed be run on a laptop as well, but it does get intensive. It is using, I usually do 500 generations per epoch. That's 500 programs, right? That it writes every, I don't know, 10 milliseconds or something like that, executes all 500 of them, and then has to rank their fitness. The longest, the most time-intensive part of this is executing each program. Why? What if one of those programs is an infinite loop, right? Well, it's going to run until it gets terminated by the program's constructs. That could take quite a few milliseconds. I don't know, maybe 100 or a little more. It's doing that 500 times. So there's a lot of time commitment in executing the system, and you do want a powerful system. So the second part of the question, can it take advantage of parallel processors? Yes. So the initial version of the system only ran on one core. The modern version of it currently runs on all the cores on the system that's available. It is using the C# parallel library, which will take advantage of all the cores on the computer. So that does help. Could you also run this with a GPU unit? Yes, I've had people offer their assistance. I've never actually adapted it to run on a GPU, but certainly as computers get faster, which I'm very much looking forward to, I think the system could show even more promise with faster computers.
Great. We've got two more questions. Can it generate a program to replicate itself?
Why does everyone ask that? That's a good question. So, can it write a program to replicate itself? Theoretically, yes. It's using a Turing complete programming language. So it can theoretically create any program that your brain can probably comprehend, because our brains work on, I believe, well, maybe not everyone would agree on this, computational activity. Maybe there's more to it. I won't get into that. Again, that's philosophy. We're crossing the line. Yeah, so I think that's but would it realistically be able to do that? You would have to write the test cases that would tell it how to do this. I wouldn't even know where to begin with that. So one idea I did have with this would be to break that down into submodules, which is what I was talking about on the last slide. In order to produce a program that would itself produce programs, you would start with, I don't know, maybe addition of numbers, maybe being able to store a string of values in an array could be a start. I'm not really sure. You would also need a compiler and an interpreter. It would have to generate that, right? So it's very complex.
Great. And the last question, what resources, books, or websites do you suggest for me to learn more about this super interesting stuff?
Okay, so we'll first start, if you go to my website, not to self-promote, but I have articles on a lot of these topics. So as I mentioned, I'm extremely passionate about artificial intelligence. And when I say that, I mean far outside of machine learning. I have done plenty of machine learning research as well, which is on my blog too. But I also, I always try to let people know there's a whole world of AI. outside of machine learning, there's symbolic AI, there's logical AI, there's cellular automata, there's genetic algorithms, evolutionary computation, conversational UI, expert systems like Watson and IBM. There's so many, AI planning. There's so many fascinating areas of AI yet to explore that haven't even begun to make the breakthroughs that machine learning has already made. So do check all of this out. We need researchers in these other areas too. So my website is one place to go, at least for a start. Another great place, like Joe was mentioning, is Udemy, and also Udacity and Coursera. Those are great places too. As far as books, I'd have to get back to you on actual books, but there are, of course, there's the famous artificial intelligence, I can't remember the name of the actual book, it's on my iPhone though, that all the colleges make you read for the first time. It's fantastic. I'm sure someone's going to post it in the chat, the name of that textbook. I love that book because it actually has Hunt the Wumpus in it, which is actually a small research project I'm working on right now to implement an AI computer player that can play Hunt the Wumpus. So yeah.
Yeah, a couple people are saying a modern approach.
Thank you. That's the one.
Yep. All right, well, thank you so much, Corey. I'm gonna hand it back off to Rama, who I think she has a one final question for you. So thank you. I'm gonna get started on my AI. Rama, you wanna take over?
Yep. Sorry, I was just trying to unmute myself. So thank you, Corey. I think it was an awesome presentation, and it was refreshing, completely a different way of thinking about it. So thank you so much. So I had, one final question for you. This research, because you said you've been doing it for a long time too, just curious to know whether this research is part of what you're doing at Bloomberg, or is it being adapted there, or is this an independent research that you're doing on your off time? I don't know how much off time you'd have if you are actually working in Bloomberg.
Right.
So.
All right, so how would everyone feel if I said I can't talk about that?
Okay.
No, I'm just kidding.
All fair. No problems.
No, actually, this is extracurricular. So I've been doing this research before my work at Bloomberg. I've been doing this for, I've only been at Bloomberg for about 2.5 years. So I've been doing this much longer than that. This is outside my work. However, my company, great place to be, great place to work. If anyone is looking for software development roles, come talk to me because we are hiring. But Bloomberg actually supports me in helping to give these talks and getting my papers out there. They helped me speak at Grace Hopper. In 2018, I actually spoke and presented this topic. So they're very supportive of it.
Awesome, awesome. And thank you so much for sharing this passion of yours and your research with us. So thank you.
Thank you.
So I think with